I hope I'm audible. Let's wait for 5 minutes so that if anyone wants to join, can join. I hope my screen is visible. Okay. So let's start with true false type problems. So today we'll be discussing some problems related to orthogonal projection and orthogonal space. So let's start with the true false problem. State whether the following are true or false. One. Let V be a Hilbert space. Let V Hilbert space. And W be a closed subspace of V. For X belonging to V, we denote PXW to be the distance of x from W, which can be formally written as infimum norm x minus W for every W belonging to the space W. We say that x is an element and x is perpendicular to the space W if the inner product of x with small w is equal to 0 for every w in W. So this is how we we can say how we define orthogonality between a point and a space. Now, if they are saying that if x minus w, where w is some element in W, this is perpendicular to W, then norm x minus w is gives us the distance. The solution. Now we are given that x minus w is perpendicular to W. That means for any z in W, for any element in W, the inner product of that element with x minus w should be 0. Hence, x minus w is perpendicular to W. This implies the inner product x minus w with any point z is equal to 0 for every z lying in the space W. Now, since W belongs to W, this implies norm x minus W is obviously greater than equal to the infimum x minus W, and which is by definition distance. So we have one side of the inequality. If we prove the other as well, therefore norm x minus W greater than equal to distance in x and W. If we prove that this norm is less than equal to the distance as well, then we'll get the equality. Now, let's mark this let's mark this one as equation 1. Now, for any arbitrary y in this space W, we have norm x minus W square. So I can add and subtract y in between. And basic in a norm property that since norm square is nothing but the inner product of x with x, we can open this norm square and we'll end up getting W square plus 2 times inner product of x minus y with y minus time. Now I can write this as minus y square plus y minus w square plus 2. So I want to make it something related to norm y minus w. Let's see how. So I can write it as y minus w since I can take minus outside, so we'll get y minus x, y minus w. It's just the basic properties of the inner product. And this is equal to x minus 2. Now I'll write, I can add and subtract w over here. So I'll get y minus w plus w minus x, y minus w. So this this term gives us 2 times norm of y minus w. So that will give us minus norm y minus w square minus 2 times inner product, or if I write it plus, get x minus w, y minus w. Now, since this y and w both are elements of the space subspace W, their difference also belongs to the space W, and hence by equation first, this is equal to 0. So this is equal to norm x minus y square, y minus W square, since think I think my iPad got disconnected. Please wait for 2 minutes. Okay. So yes, this is because y minus W is an element of W, and hence we can use equation first. And this is obviously less than equal to norm x minus y square. Therefore, we got norm x minus w. This is less than equal to norm, or I can write that. Norm x minus y square is greater than equal to norm x minus w, or we can remove the square as well, for every y in w. Now that means this norm x minus w is a lower bound, and since we know that infimum is the uh, greatest lower bound, this implies infimum y belonging to w norm x minus y. This is also greater than equal to norm x minus w. Hence, we get norm x minus w is less than equal to distance between x and w. That is what we wanted. Yes, distance. Therefore, by second and third, norm x minus w is equal to distance between x and. Therefore, the given statement is true. I hope this solution was fine with everyone. The main important fact thing we used in this proof is that this one, that if x minus w is orthogonal or perpendicular to the space w, then x minus w inner product of x minus w with and z should be equal to 0 for every z in w. If you have any doubt, please you can ask. Otherwise, let's move to next question. With the notations as above, in the previous question, if x minus w is perpendicular to w, then norm w should be less than equal to norm x. So let's see if this is true or false. We are given that x minus w is perpendicular to w. This implies the inner product of x minus w with w also. This is equal to 0. Clearly because w belongs to the space w. And this tells us that just by the properties of the inner product, I can split it. This is equal to 0. Therefore, norm w square, this is equal to mod x w, which is always less than equal to modulus x w, because every real number is lesser than equal to its absolute value. This is less than equal to, by Cauchy-Schwarz inequality, Schwarz inequality. Therefore, dividing both sides by norm w is less than norm x. That is what they were saying. Therefore, the given statement is true. I hope this solution is fine. If you have any doubt, please let me know. This was just basic use of the properties of the inner product, the way inner product is defined, and the Cauchy-Schwarz inequality. Also, the definition of orthogonality. Next, we'll be using a characterization of the orthogonal projection. So let me recall. If W is a subspace of some space V, and P is a linear transformation, continuous linear function from V to, or instead of V, let's write it H. Let's write it where V is some inner product space from V to W is such that PV, this is belonging to W for every V in W. Obviously, this should be well defined. And this satisfies the fact that P inner product of PV with W is equal to inner product of V with W for every W in W. Then we say that this P is orthogonal projection of V on W. So using this characterization, we'll be solving next problem. Let's see question number 3. Let W denote the subspace of all even functions. Functions in L2 minus pi to pi, and P denotes the orthogonal projection of orthogonal projection of V onto W. Now, if T is equal to sine T cos T, but every T in minus pi to pi, this is how we define. If clearly this will belong to L2 minus pi to pi, then they are saying that PF is 0. Now, firstly, we need to see how does this P look like. Now, see, W is all those F in L2 minus pi to pi such that F is even. And P, F maps to some G which is in W. Now, if I define, so we all know that Ft, if I define Ft, so if since for every f in L2 minus pi to pi, I can write Ft as f of t plus f of minus t by 2 plus f of t minus f of minus t by 2, where this is an even function and this is an odd function. Now, if I define P from L2 minus pi to pi to the space W such that P of f, now P of f is a function in W, P of f at any point t is equal to ft plus f minus t by 2. Clearly, P of f is an even function, so this P is well defined. All we need to show is that this function, this P is an orthogonal projection. That means by that characterization we discussed earlier, if so I claim that inner product of PF with G is equal to inner product of F with G for every G in W. If this holds, then surely this P is an orthogonal projection. So, and in L2 space, we know that the inner product is nothing but the integral. So let's start with the LHS. This is inner product of PF with any let G belonging to W be arbitrary. So this is integration minus pi to pi PF t gt dt. So this is equal to this minus pi to pi, just applying the definition of PF of minus t by 2 gt dt, splitting the integral by ft gt by 2 plus minus pi to pi f minus t. Now here instead of gt, I'll write g of minus t because g belongs to W and hence it is even. Since g belongs to W, this implies g is even function. That means g of t is equal to g of minus t. You'll get to know why I did this in the next step. Now this is minus pi to pi 1 by 2 ft gt dt plus minus pi to pi 1 by 2 ft gt dt, because for definite integral we know that a to b fx dx is equal to integration a to b f a plus b minus x dx using this property of definite integrals. Now this is equal to inner product of f with g. That is what we wanted. Just RHS. Therefore, PFG is equal to F G for every G in W, and hence by the characterization of orthogonal projection, hence by the characterization of orthogonal projection, P is an orthogonal projection of V onto W. Now we need to show that if projection of this F is zero. Let's see how this implies. Now for Ft equals to sine t cos t, we have Pft is equal to Ft plus f of minus t by 2. This is 1 by 2 sine t cos t plus, and since we know that sine minus t is minus sine t and cos minus t is cos t, this is equal to 0 for every t in minus factor pi. Therefore, this f is mapped to 0 function. Hence, the given statement is true. In fact, if we can write our space V in as some direct sum of two subspaces, and we want, that means for every V in V, this small v can be written as W1 plus W2. In that case, PV mapped to W1 serves as the orthogonal projection on the space W1. And similarly, PV mapped to PV mapping to W2 for every V in V, this serves as orthogonal mapping on the space W2. Now here clearly we can write this space L2 as some direct sum of the space of all odd functions and even functions. That is why we selected this type of P. And eventually, by the characterization of the orthogonal projection, we could prove that yes, this will be our orthogonal projection. And rest was to just apply this on the function, given function f. So the main important thing, fact is that every function can be written as sum of odd and even functions. Secondly, the characterization of orthogonal projection. Hope this was fine. If you have any doubt, please you can ask. Okay, if not, let's move to next question. What's question number? Let K be a closed convex subset of R2. Let K subset of R2 be a closed convex set for any x in R2. Let Let pkx denote the point in K which is closest to X. Let pk denote the point in K which is closest to X. Then they are saying if we take K to be the closed unit ball, let K be the closed unit ball. In that case, our pkx is given by x by norm x for every x in R2. Let's see whether this is true or false. Now suppose this is true. Suppose pkx is equal to x by norm x. So if y is some element in K, such that if y belongs to K, K is the closed unit ball, I am taking y to be in the interior of K, be such that its norm is strictly less than 1. So by the definition of pk, pk is this closest point in K. Now since y is in K itself, therefore this pky should be equal to y. This is by the definition of pk. But if first is true, in that case, we are getting pky is equal to y by norm y. Which is strictly greater than this. See, norm y is strictly less than 1, so 1 by norm y is strictly greater than. Which gives us a contradiction. Hence, the given statement is false. So if this is fine, let's move to the next question. Let pk be as defined in the previous problem, and k, so k was some closed and convex set. In the for this case, for this problem, we are taking a k to be all those points in R2 such that x1 plus x2 is equal to 1. So this is basically a straight line. So if O denotes the origin, then PKO, that is the point in K nearest to the origin, is given by 1 by 2, 1 by 2. So we all know, let's firstly plot the points of K. K has the points which lie on the line x1 plus x2 equals to 1. This is a straight line. All points lying in this line are in K. We need to find a point on this line which is nearest to the origin. So we all know that this is the sum. If we draw some orthogonal or we can say perpendicular from the line to the origin, that point P will give us the nearest point. Now, since this point is perpendicular, if I denote this point as some A, in that case, the vector OP is perpendicular to the vector AP. That means the inner product, now OP is x comma y minus 0 comma 0 and AP is y comma 0 minus x comma y. This should be equal to 0. That is inner product of xy with 1 minus x and minus y. This should be equal to 0. So by the definition of inner product on R2, this is x times 1 minus x plus y times minus y is equal to 0, or x minus x square minus y square is 0. Also, this point P lie on the line. Also, since this point belong to the set K, that means x plus y equal to 1, or I can write y to be equal to 1 minus x. So I can replace y by 1 minus x in equation first. X minus x square minus 1 minus x whole square equals to 0. This is x minus x square minus 1 plus x square minus 2x equals to 0. So eventually I'll end up getting x times 2x minus 1 equals to 0. This implies either x is equal to 0 or x is equal to 1 by 2. So in this case, y is 1 and in this case, y is 1 by 2. So the minimum, the point, so from here we get p is equal to 0 comma 1 and from here we get p equals to 1 by 2, 1 by 2. So the point from which the distance between origin, the point from where the distance with origin is minimum of these 2 points, that will give us our that will give us our PKO. Now, the distance between 0, 0 and 0, 1, where this is 0, 1 square, which is 0 minus 1 times 0 minus 1, which is 1. And here the distance is nothing but 1 by 2. Since the distance over here is the minimum one, therefore PKO is 1 by 2 comma 1 by 2. Therefore, the given statement is true. That is what it was saying in the statement. Therefore, the given statement is true. I hope this is fine. If you have any doubt in any step, please let me know. So let me recall what we did in problem first. These this type of calculation. Yeah, whatever we did here, let's mark this as star. We'll be using it. Okay. So here we haven't done any. We haven't used anywhere the fact that W is some subspace and x minus w is perpendicular. Here, this is just basic properties of inner product. So we'll be using this again in next question. So I marked it as star. I think my screen is disconnected. I hope it is visible now. Okay. So yes, we'll be using this type of calculation again. So which is basically just the properties of inner product space. Let's move to next question. Next. Let K be the space of all those points x1, x2 in R2 such that x1 is greater than equal to 0 and x2 is also greater than equal to 0. That means we are in first quadrant. For all, then they're saying that for all x in R2 such that x1 and x2 is strictly negative, we have pkx, that is the nearest point in K to X is equal to 0. So let's see. This is our K, and they're saying that if I take any point from the third quadrant, where X and Y both coordinates are negative, in that case, PK, the nearest point in K from this point XY should be 0. Let's see if this holds or not. Now let's Z get some Z which is equal to Z1, Z2 belonging to K be arbitrary. And X belongs to the x is such that both the coordinate components are negative, and x equals to x1, x2 being such that x1 is negative and x2 is negative. So if I prove that the distance between this x and z is greater than equal to the distance between x and origin, for since k z is arbitrary element in k, in that case the nearest point, because any point z in k is farther from the point from the origin, therefore the nearest point will turn out to be origin. If we could prove something like this, then the given statement is true, or else it is false. Uh, so the inner product of x minus the origin with z minus the origin is equal to x1, x2, z1, z2, which is x1, z1 plus x2, z2. Now, since x1, x2 are negative and z1, z2, since this is in k, so both are strictly positive, so eventually this sum is less than equal to 0. Now, as done in star, and go back there and see, we will get, since 0, 0 belongs to k, not, we'll get the distance between x and origin. This is less than equal to norm x minus z square, and then we had some inner product of this form, which is, we know that this is negative. This is less than equal to norm x minus z square for every z in k. Therefore, norm x square, or let's write it x minus 0, x minus o, where o denotes the origin, this is less than equal to norm x minus z for every z in k. Again, since infimum is the greatest upper bound, we'll get norm x is less than equal to infimum z in k, norm x minus z, and by definition, this is pk x. Norm x minus o. So origin, so the distance between x and any point in k is always greater than equal to the distance between x and origin. Therefore, by definition of pkx, pkx should be equal to the point origin or 0, 0. Therefore, by the definition of pk, pkx should be equal to origin. Therefore, the given statement is true. I hope the solution is fine. If you have any doubt, please let me know. Okay, if you do not have any doubt, we can move to next question. Let H be a Hilbert space. Hilbert is name, so I should have H capital. Hilbert space and Xn by n be two sequences in H such that Xn converges weakly to X and Yn converges weakly to Y, both in the space H. Then they're saying that in this case, the inner product Xn Yn should converge to X. So this actually does not happen if we take H is equal to L2 space. We all know that L2 is a Hilbert space. This is the space of all those sequences Xn such that they are square summable. We know that H is a Hilbert space. And if I take sequences and if we take Xn and Yn both to be equal to this sequence En, we take Xn equal to Yn equal to En, sorry, En in N, where En is the sequence in L2 that has 1 at nth position, 0 elsewhere. In that case, we know that this Xn and Yn will converge weakly to 0 in L2. This we have proved earlier, if you remember in previous classes. So if the above statement is true, the above statement is true, in that case, the inner product of Xn with Yn should converge to 0. But this is nothing but norm En square, because Xn and Yn both are equal to En, and this is equal to 1. The constant sequence 1 can never converge to 0. Therefore, the given statement is false. Hence, in Hilbert space, if we have two sequences that converges, if both are converging weakly, in that case, we cannot say anything about the convergence of inner product. Whereas, we'll see in next question that if we have one strong convergence and one weak convergence, in that case, we will get this the inner product converging to the limit xy. So if we have at least one strong convergence, that will be helpful for us. Let's see. Move to the next question, where we'll have one weak and one strong convergence. A. Let H be a Hilbert space. I'll just write HS for Hilbert space. And Xn, Yn are sequences in H such that this xn is converging weakly to some x in H, and yn is converging strongly to y in H. Then the inner product x and yn converges to x. We will see that the statement is true. Now consider modulus x and y minus xy. This should converge to 0. Let me just add and subtract y here. So I can write it as modulus x n y n minus y plus x n y minus xy. This is equal to next I'll be adding subtract no, I don't need that. So this is x n y n minus y, and next two terms we can take y common. So this is x n minus x with y, which is obviously less than equal to modulus x n y n minus y, just the basic triangles inequality. Next we'll be using the Cauchy squads because we have modulus of inner product. This is less than equal to norm xn, norm yn minus y, and we'll keep the second term as it is. Now let's denote this as a1 or an and this as bn. Now if an and bn both converges to 0, then we are done. Now this an is less than equal to some n times norm yn minus y. Why? Because xn is convergent, weakly convergent, and hence bounded. Xn is weakly convergent in H, hence bounded in H. And since yn converges strongly to y in H, this converges to 0 as n tends to infinity. Also, since xn converges weakly to x, we have xn minus x converges weakly to 0 in H. That means for any bounded linear functional f defined on H, this should converge to 0. Now we know that since f from H to R, f uh, z equals to inner product zy is a bounded linear functional. To H star dual of H for every f in H star. This implies we can replace this z by x n minus x comma y. This converges to 0 as n tends to infinity. Therefore, Bn, which is nothing but modulus of this inner product, this would converge to 0. And hence, our inner product x and yn minus the inner product xy converges to 0. Therefore, x and yn converges to xy. And hence the given statement is true. I hope this solution was fine. Mainly we have used the Cauchy squads Then we have used the fact that weak convergence implies for every the basic definition of weak convergence. Okay, so if you do not have any doubt, we can move to next question. Let H be a Hilbert space and Xn be a sequence in H such that Xn converges weakly to X. Assume that norm Xn is less than equal to 1 for every n in N and norm X is equal to 1. Then they're saying that in this case, Xn should converge to X strongly in H. So let's see whether this is true or not. Okay. Now, since Xn converges to X weakly in H, this implies for every bounded linear functional f in H star, in the dual space of H, we have Xn converges strongly to F. So this is just convergence in R. This implies modulus fx is equal to limit n tending to infinity mod fxn This is less than equal to lim n tending to infinity norm f norm xn, because we know that x since f is a bounded linear function, mod fx is less than equal to norm f norm xn for every n, sorry, for every x in h. And since we don't know whether this xn is norm xn is convergent or not, we cannot we should type lim inf. So this is equal to, so therefore mod fx, this is less than equal to limit n tending to infinity. You can take this norm f outside because it is independent of n, and for every f in h star. So this implies supremum f belonging to h star minus 0, or in fact, I should write it as supremum f belonging to h star such that norm f is less than equal to 1. Modulus fx in this case will be less than equal to limit inferior n tending to infinity norm xn. Now we know that this is equal to norm x. We had done such problems earlier a lot. So this implies norm x. This is less than equal to. This implies, since we are given that norm x is equal to 1, is less than equal to norm xn. Also norm xn is less than equal to 1 for every n. So this is less than equal to 1. Since we are squeezed between 1 and 1, so this implies, moreover, we can write it to be less than equal to limit superior norm xn. Since norm xn is less than equal to 1, so the limit superior and limit inferior both will also be less than equal to 1. Now, since we are squeezed between 1 on both the sides, so we'll get limit inferior is equal to limit superior. And in that case, we know that this is equal to limit n tending to infinity norm xn. This is equal to 1. Therefore, the sequence norm xn, this converges to 1 in R. We need to see whether this is strong convergence in H or not. So now, norm xn minus x square, this is equal to, just by the fact that norm x square is inner product of x with x, this is xn square, this norm x square minus 2 in product of x and x. Now, since xn converges to x weakly, this term, this will form a bounded linear function, and hence this will converge to 2xx. And also we know that this norm is converging to 1. So this is converging to 1 plus norm x, we know that it is equal to 1 minus 2 times x comma x, which is basically the norm of x only. So this is 2 minus 2 times norm of x square, which is 1. So this is 0. Therefore, norm xn minus x square is converging to 0. This norm is in H, hence xn converges strongly to x in H. Hence the given statement is true. I hope this solution is fine. If you have any doubt, you can ask. Okay, if not, let's move to next question. So we are done with the true false. So the following. Question number 10. Consider the space H subset of R3 defined by H is equal to all those points x, y, z in R3 such that x plus y plus z is equal to 0. That means we are in some plane. Compute the matrix the matrix which represents the orthogonal projection. Matrix represents the orthogonal projection of R3 onto H with respect to the standard basis. So for that, we know in order to find the matrix representation of a linear transformation, we need to find the image of the basis elements. So basically, if P is the projection, suppose P from R3 to H is the orthogonal projection, is the orthogonal projection of R3 onto H, we need to find P of 1, 0, 0, P of 0, 1, 0, and projection of 0, 0, 1. So now suppose if P E1, so this is E1, E2, E3 is equal to some vector x1, x2, x3 in H, then clearly x1 plus x2 plus x3 should be equal to 0. That's how we define H. Also, by the characterization of the orthogonal projection, we should have PE1 inner product of PE1 with Z is equal to inner product of E1 with Z for every, so since we have H, I'll write it as H, for every H in H. That means if H is some H1, H2, H3, we should have X1 times H1 plus X2 times H2 plus X3 times H3. Now since E1 is 1, 0, 0, so this is just H1. Also, since yes, since H is in capital H, I can replace this H3 by minus H1 minus H2. Since H is in H, this implies this H3 equal to this. So this implies x1 times h1 plus x2 times h2 plus x3 times minus h1 minus h2 minus h1. This is equal to 0. This h1 times also h1 times x1 minus x3 minus 1 plus h2 times x2 minus x3. This is equal to 0. Now since h equals to h1, h2 and minus h1 minus h2 belonging to h is arbitrary, this implies h1, h2 belonging to r are arbitrary. This implies, I mark this one as equation 1, this one as equation 2. Equation 2 holds for every h1 and h2 in R. So in that case, we should have x1, right, from the first component, x3 equals to x1 minus 1, x1 equals to x3 plus 1, and x2 equals to x3. Third, using third in first, we get x3 plus 1 plus x3 plus x3. This is equal to 0. This implies x3 is minus 1 by 3. And hence, x2 is also minus 1 by 3. X2 is minus 1 by 3 and x1 is, in that case, you'll get x1 to be equal to 2 by 3. Therefore, P100 is 2 by 3 times E1 minus 1 by 3 times E2 minus 1 by 3 times E3. Similarly, you can find the images of E2 and E3 and you'll get E2 will be, you can try this yourself, minus 1 by 3 E1 plus 2 by 3 E2 minus 1 by 3 E3 and E3 will be equal to minus 1 by 3 E1 minus 1 by 3 E2 plus 2 by 3 E3. And hence, the matrix representation of the orthogonal projection with respect to the standard basis beta, which is just E1, E2, E3. This is 2 by 3, minus 1 by 3, minus 1 by 3, minus 1 by 3, 2 by 3, minus 1 by 3. This is how you can find the matrix representation. The main important point was the fact that the characterization of the orthogonal mapping. Yeah. If you have any doubt, you can ask. Not, let's move to next question. Okay. So question number 11. Compute the orthogonal projection of the space L2 onto the closed subspace of functions vanishing on interval minus pi to 0. So, okay, so we need to find the orthogonal projection P from L2 minus pi to pi to some h, where this h is the space of all those functions in L2 minus pi to pi that vanishes on the interval minus pi to 0. That means f is 0 on minus pi to 0. Now, if I define P f is equal to f times characteristic function on the interval 0 to pi, in that case, obviously every function f will be mapped to some function g, which is 0 and minus pi to 0, because this characteristic function, this is just the product. So this p is well defined. Moreover, any function vanishing on the interval minus pi to 0 can be written in this form. So this is an onto linear transformation. So all we need to see is whether this is an orthogonal projection or not. For that, it should satisfy the uh, characterization of the orthogonal map. So we claim that the inner product PFG is equal to FG for every G in H. If this holds, in that case, this P will be the orthogonal projection. So let uh, let F belongs to, or F belongs to L2 minus pi to pi. We define PF like this. Let's start with the LHS. The inner product of PF with G, this is equal to minus pi to pi F times PF times G. G, this is minus pi to pi. PF is F times characteristic function on the interval 0 to pi times G. So this function overall is 0 on the interval minus pi to pi. So I can reduce this integral to 0 to pi. And in this interval, the characteristic function attains value 1. So this is just fg. Now since g belongs to the space h, it vanishes on the interval minus pi to 0. So I can write it as plus 0, which is minus pi to 0 times f. So this is just minus pi to pi fg, which is the fg. Therefore, pf mapped to f times characteristic function defined on the interval 0 to pi defines the orthogonal projection of L2 minus pi to pi onto H, the space of all functions vanishing on the interval minus pi to 0. I hope this is fine. Okay, then let's move to next question. Let Z be the space of all those points in R3 such that 2x equals to 4, y equals to minus z. Compute the space Z per. That means the orthogonal of Z. We know that for every x belonging to Z per, the inner product of x with Z is equal to 0 for every, so let me write it as small z, for every Z belonging to Z. Now, if Z belongs to capital Z, and Z1, Z2, Z3, this is equal to Z belongs to Z. So by the definition of the space Z, we'll get Z3 equals to minus 4 times Z2 and Z1 equals to 2 times Z2. So in that case, we'll get 0 is equal to, if x is some x1, x2, x3 times, I can write this Z as taking Z2 outside, 2, 1 minus 4, this minus 4, which is equal to 2x1 plus x2 minus 4x3 times z2. Now, since z belonging to z is arbitrary, this happens for every z2 in R. This implies 2x1 plus x2 minus 4x3 is equal to 0. Therefore, Z perp is set of all those points in R3 such that 2x1 plus x2 minus 4x3 is equal to 0. I hope this solution is fine. If you have any doubt, you can ask. Okay, if not, let's move to next question. Let V be a Hilbert space. and W subset of V be a closed subspace space of V or for some fixed U in V, define the continuous linear functional I from W to R by and any W is just the inner product of W with U for every W and W. Then compute its Hanbanach extension. So we'll be using the orthogonal projection of V onto the space, the subspace W to find this Hanbanach extension. Let's see how. Suppose P from V to W be the orthogonal projection of V onto W. If we define phi tilde from V to W, sorry, V to R, where phi tilde V is equal to PV time inner product of PV with U for every V in V. I claim that this phi tilde will serve as our Hanbanach extension. Now, if W belongs to W, in that case, obviously PW will be W because it's in W itself. Its orthogonal projection is itself. And phi tilde W, this is WU, which is by definition equal to phi W. This implies phi tilde. Obviously, phi tilde is boundary linear functional because PV is again an element of W, which is in V itself. So this phi tilde restricted to W is equal to phi. So we claim that norm phi tilde is equal to norm phi. Moreover, I wanted you to try this yourself because we have done a lot of problems where we evaluate norm of operator. So okay, I'll do it again. Subclaim 1, this norm phi is equal to norm of PU, where U is the fixed vector in V and PU is its projection. Now, since WU, this is equal to UW by symmetry. This is equal to PUW for every W and W just by the characterization of the orthogonal map, which is going to be written as WU. Therefore, phi w can be written as the inner product of w with pu. This implies mod phi w by norm phi. This is equal to mod w pu by norm w. Then by Cauchy squares, this is less than equal to norm pu. For every w in w. Also, uh, since so from here you'll get that norm phi is less than equal to norm pu, and since for every u belonging to v, pu belongs to w, then mod phi pu by norm pu. This is obviously less than equal to norm phi, and phi pu from here you can see that phi pu is nothing but norm pu square. So this is just norm pu less than equal to norm phi. And hence norm phi is equal to norm pu. Similarly, you can see this yourself. I would like you to try it yourself. Using exactly the same method as we are doing here, you will get that norm phi tilde is equal to norm pu, and hence norm phi is equal to norm phi tilde, where phi tilde restricted to w is equal to phi, therefore phi tilde, which was defined from v to r, phi tilde v is pv, inner product of pv with u. This is the Banach extension of phi. I hope this solution is fine. If you have any doubt, you can ask. So yeah, we have used the orthogonal projection in order to find the Banach extension of a bounded linear functional defined on the space W. Okay, let's move to next problem. Let H be a Hilbert space and A be a bounded linear operator from H to H, be such that for every x in H, the inner product of AX, obviously AX is an element in H, with X, this is less than equal to H. Let lambda be some positive real number. Assume that lambda I minus A is surjective. That means onto show that the operator lambda I minus A is invertible in LH and norm lambda I minus A inverse is less than equal to 1 by lambda. So since we are given that lambda a minus I is surjective, if we prove that this is injective as well, then we can find its inverse. Further, we need to show that this is invertible in the space LH. That means that inverse should be an element, should be a bounded linear operator as well. That means continuous linear transformation. Obviously, we know that inverse of a linear transformation is again a linear transformation. So the main important point we will be left with will be to show that lambda I minus A inverse is continuous as well. So for that, we'll be using open mapping theorem and further using basic properties of the inner product, we'll be showing this inequality as well. So let's see how we do that. Now, since lambda I minus A is surjective, if lambda I minus A is injective as well, then we can find a linear transformation, need not necessarily be a bounded linear operator, lambda A minus I inverse from H to H. Now suppose, so in order to show that it is injective, we'll show that its kernel is singleton 0. Suppose if some x belongs to kernel of lambda I minus A, in that case we have lambda I minus A x is equal to 0. That means Ax is equal to lambda x. So since Ax times x, this is less than equal to 0, we'll get lambda x less than equal to 0, lambda times norm x square is less than equal to 0. Now since we are given that lambda is strictly positive, we must have norm x square less than equal to 0 because lambda is strictly negative, and this holds only if norm x is 0, if and only if x is 0. Therefore, kernel A minus, sorry, lambda I minus A, this is singleton 0. Therefore, lambda I minus A inverse from H to H is a linear transformation. Moreover, it is bijective. Now, let U be an open set in H, then we need to show that lambda I minus A, so this inverse, the inverse, this is lambda I minus A, U is open. Why? Because lambda I minus A is surjective bounded linear operator. This implies by open mapping theorem, this is an open map, and hence lambda A I minus A U is open in H for every open set U in H. And hence lambda I minus A inverse is continuous linear transformation. Therefore, lambda I minus A inverse belongs to the space of all bounded linear operators defined on Hilbert space H. Therefore, lambda I minus A is invertible in LH. Next, we need to so that its norm is less than equal to 1 by lambda. Now, let y belonging to H be arbitrary. Since lambda I minus A is surjective, we can find some x in H such that y is equal to lambda I minus A at x. This implies the inner product y with x. This is equal to lambda I minus A x x. This is lambda x minus A x x. This is lambda times x x minus A x x. Lambda norm x square minus Ax x. Now, since this inner product is negative, and its minus will turn out to be positive. So this is a positive term. Therefore, this is greater than equal to x square. This minus Ax x. This is positive. Therefore, we get lambda times norm x square less than equal to mod yx. Sorry, inner product of yx. This should be equal to mod by x because if I mark this as star by star, this is positive. This inner product is positive because obviously norm x square is positive, and we are given that the inner product of ax with x is negative, so minus ax x is positive. So since this is positive, it is equal to its absolute value. And now we will use the Cauchy squartz inequality. This is less than equal to norm by norm x. Dividing both sides by norm x, we'll get um, get norm x is less than equal to 1 by lambda norm y. Y was arbitrary, or this implies since this x is equal to a minus lambda I inverse y, this by norm y is less than equal to 1 by lambda for every y belonging to h minus 0. So by the definition of operator norm, the norm of a minus lambda I inverse, this is less than equal to 1 by beta. That is what we needed to prove. So I think today we ran out of time. I was left with one more problem, but that will take some time. I'll not be able to finish that in 8 minutes. So I guess this is it. If you have any doubt in this problem, you can ask. I'm waiting for at least next 8 minutes. I'm here. You can ask if you have any doubt. Okay, if you do not have any doubt, we can end this session. So we'll be meeting next Friday. Hopefully, you'll be. If you have, you can go through today's lecture material within this week time, and if you have any doubt, you can ask me in the next class. Okay.